Okay, so moles are one of the most important things that we learn in this class. You'll find that moles are part of everything we'll be doing. So I want to make sure you understand them now and that you have plenty of marination time. So what is a mole? Well, a mole is a unit of measurement used in chemistry. So like you can buy a dozen eggs. We know that a mole is equal to Avogadro's number of atoms, molecules, formula units, things like that. So this video is by TED Ed. I would highly recommend watching it. It gives you kind of a better perspective and understanding of what the mole is. And this is usually how we abbreviate it. We just kind of leave off that E. So 1 mole of any substance contains this number, which is Avogadro's number of representative particles, atoms, molecules, and formula units. So to find the number of atoms in an element, we need to recognize that first that we have an element and that 1 mole of any element is equal to Avogadro's number of atoms. So 1 mole of iron, 1 mole of carbon, 1 mole of nickel, 1 mole of magnesium. It doesn't matter what the element is, it's going to be equal to 6.02 times 10 to the 23rd atoms. So I have an example here. I have 2.5 moles of tungsten. We know 1 mole of tungsten is equal to Avogadro's number of atoms. So we're going to multiply the top, divide the bottom, and we find it to be 1.51 times 10 to the 24th atoms of tungsten. So let's look at this next practice problem. How many atoms do you have given 0.75 moles of magnesium? So I want you to think back to when we did a dimensional analysis in the factor label process, and I want you to remember top, bottom, cancel. So if I want moles of magnesium to cancel, they need to be on the bottom, and that we know 1 mole is equal to Avogadro's number of atoms. So I'm going to take 0.75, and I'm going to multiply that by Avogadro's number. And I found 4.52 times 10 to the 23 atoms of magnesium. Well, if we're trying to find the number of molecules in 1 mole of a compound, that's the same idea. So 1 mole of any compound is equal to Avogadro's number of molecules. Okay, so before 1 mole of any element is equal to Avogadro's number of atoms. Now 1 mole of any compound is equal to Avogadro's number of molecules. So 1 mole of water, and apparently something happened here, but we could say this is CH4. We could say this is something else. I don't know what happened to that slideshow. Okay, so 1 mole of any compound is equal to Avogadro's number of molecules. So if I have 2 moles of sodium nitrate, I'm going to start with that as my given. We know 1 mole is going to go in the bottom for top-bottom canceling, and we know 1 mole is equal to Avogadro's number of molecules, and I can solve that out. So given 0.5 moles in O2, how many molecules? We know 1 mole needs to go on the bottom for top-bottom cancel. And we know that's equal to 6.02 times 10 to the 23 molecules. So 0.5 times 6.02 E23. We find it to be 3.01 times 10 to the 23 molecules in O2. Okay, so 1 mole of an element is equal to Avogadro's number of atoms. 1 mole of a compound is equal to Avogadro's number of molecules. Well, how do we find the number of atoms in 1 molecule? Well, we're just going to count. Okay, so if I have CH4, I know that there's 1 carbon, 4 hydrogen. So 1 plus 4 is 5. So that would be 5 atoms. If I have Hc2H3O2, I have 2 carbons, 4 hydrogens, 2 oxygens. So 2 plus 4 plus 2, that would be 8 atoms. And then for 1 molecule of SO3, we have 1 sulfur, 3 oxygens, 1 plus 3 is 4 atoms. So how many atoms in a molecule of NH4OH? So we have 1 nitrogen, we have 5 hydrogen, and 1 oxygen. So that ends up being 7 atoms per 1 molecule of ammonium hydroxide. And what you're going to find is we could put these pieces together. So if I'm given moles, how many total atoms in a compound? We're going to put these two brackets together. So given 2.12 moles of CH4, we're going to start with that. Okay, so we have 2.12 moles CH4, 1 mole, that's equal to Avogadro's number of molecules. Okay, and then once we know our number of molecules, we know 1 molecule is equal to 5 atoms, so we actually end up putting two brackets together. Moles cancel, molecules cancel, left with atoms, multiplied out, and I find it's 6.38 times 10 to the 24th atoms of CH4. Okay, so let's look at this next one. We have 0.5 moles CO2, and how many total atoms are in that compound? Well, we can't go directly from moles to atoms, we have to go to molecules first. So 1 mole CO2 is equal to Avogadro's number of molecules. That's of CO2. Now we want molecules to cancel, so 1 molecule CO2 is equal to 3 atoms, so we count to figure that out. 2 plus 1 is 3. And then we're going to multiply everything on the top and divide everything on the bottom. So I found it to be 9.03 times 10 to the 23 atoms of CO2. Now this is total atoms. Let's say I wanted to know just atoms of oxygen. So instead of 3, that'd be 2 atoms of oxygen. And if it was just of carbon, I would say 1 atom of carbon per 1 molecule. Okay. Now, this part here, this is what we're going to use the most, is dealing with grams. Because in a lab, you can measure things in grams much more easily. So 1 mole of an element, it's equal to the mass listed on the periodic table. So those are called AMUs, and we often will just call them grams. So we're going to round to the 0.1. So if you look on the periodic table, you'll find 1 mole of carbon is equal to 12 grams. 1 mole of hydrogen is equal to 1 gram. Notice we're going to round chlorine. 1 mole of chlorine is 35.5 grams. So if we look at some others, nitrogen would be 14 grams. Sodium is about 23. Magnesium is about 24.3. And over time, you'll learn what these masses are very easily. So this is called the molar mass or the molecular weight of an element. More likely, we are going to deal with a compound. And so notice I renamed this as molar mass or molecular weight. We're also going to use the periodic table again. This time you're going to find the masses and multiply by the number of each atom and add them together. Some example for water, it has 2 hydrogens, and that's 1 gram from the periodic table. 1 oxygen with 16 grams from the periodic table. So 2 plus 16 would make it have 18 grams of oxygen. And that would be its molecular weight. 1 mole of hydrochloric acid, you have 1 hydrogen at 1 gram, 1 chlorine at 35.5 grams. When you add that up together, it's 36.5. Okay, so if we look at sugar, we have 12 carbons at 12 grams, 22 hydrogens at 1 gram, 11 oxygens at 16 grams. So 12 times 2 plus 22 plus 11 times 16. 12 times 12. It helps if I multiply correctly. And that ends up being 342 grams for C12H22O11. So that would be per 1 mole. Okay. And then the next one, sodium phosphate. We have 3 sodiums, 23 grams. 1 phosphorus, I'm going to round that to 31 grams. 4 oxygens at 16 grams. So that ends up being 164 grams for sodium phosphate. So I do expect you to be able to go from grams to moles and vice versa. So I have 32 grams here of water, and if I'm going to convert to moles, I need to find my molar mass, or the molecular weight from the periodic table. So just a reminder, that's where that number came from. Those are equivalent. So grams cancel, top bottom cancel, left with moles. So 32 times 1 divided by 18 is 1.78. Now this next one, given 0.5 moles of NaOH. So now I'm going to want moles on the bottom to cancel. Again, using the periodic table, that's where the 40 grams came from. 0.5 times 40 is the 20 grams NaOH. So if we look at this last one, 0.25 moles calcium chloride. So I'm going to want moles to cancel by putting those on the bottom. Calcium is 40.01 plus chlorine, which is 35.5 times 2. And so 35.5 times 2. Let's see if I could type that correctly. So the molecular weight is 111 grams of calcium chloride. So I'm going to multiply that by the 0.25 moles. So you have 27.75 moles of calcium chloride. We could also find liters of gas. 1 mole of any gas is equal to 22.4 liters. And that would be at standard temperature and pressure. So we're going to be at specific conditions for that to happen. So any compound, it could be carbon dioxide, carbon monoxide, sulfur trioxide, whatever. So I'm going to start with my 0.5 moles CO2. And if you'll notice, I wrote this problem wrong. 1 mole of CO2 should be on the bottom. And 22.4 liters should be on top. And so 0.5 times 22.4 should equal out to that 11.2 liters of CO2. So always double check that your moles cancel and you're left with liters on top. So I totally made a mistake when I wrote that out. Okay, so if I have 2 moles CH4, we're going to convert to liters. 1 mole CH4 is equal to 22.4 liters CH4. So I could just multiply these two together, and I find to be 44.8 liters of CH4. Okay, one last thing, percent composition. So the percent of a mass of an element, you're just going to take the mass of the element, this is from the periodic table, over the total mass of the compound, which would be your molecular weight or your molar mass, and then you multiply by 100 to make it a percent. So if I look at SO4, it has one S at 32 grams. The molecular weight of it is 96. 32 divided by 96 times 100 is 33%. I have 4 oxygens at 16 grams divided by 96, multiplied by 100, and it's 67%. And then I would double check that this does add up to the 100% mark. So what is the percent composition of each element C2H6? So we're going to look at percent of H and percent of C. So we're going to find both. So 2 times 12, carbon is 12. The molecular weight of this whole thing is 30. So 24 divided by 30 is 80%. Without doing the math, I should realize that hydrogen is only going to have 20. But let's practice this. 6 times 1 over 30 times that 100 ends up being 20. And it does indeed add up to 100%. Now this is the most important slide of the whole thing. In fact, I would put this on a separate sheet of paper so you can easily pull this out. This is relating everything together in 1 mole roadmap. So we can go from grams to moles using the molecular weight. We can go moles to atoms using Avogadro's number, and 1 mole to liters using 22.4. Now that's for an element. If we have a compound, there's one additional step. So we could go grams to moles the same way, moles to molecules the same way, but now molecules to atoms we are going to have to count. So that's to say count. And then here we have again the liters going up. So notice the mole roadmaps are different depending if you have an element or a compound. This actually puts all of the notes together into one slide. So this I put on my help sheet and I would have it easily accessible. So I have some practice worksheets available for you. And then here's some resources that can help you with all of this. And then some videos. So I want you to become experts at the mole. It will really help for when we start stoichiometry in January.